we have been talking about probability, which is the likelihood that something will happen. Now we're moving into a connected region of math called statistics. So this is lesson E. We're talking about some basic statistical measures. The information we're talking about is coming from your textbook, lessons 8.3 and 8.4. So first, what is statistics? A course that some of you will be taking next year. Some others of you maybe a year after that. We offer it at the regular and also the AP level. So statistics is a kind of math where we gather data and then analyze that data. So we study trends in a smaller group of data called a sample to understand what's happening in a larger data set. So for example, like when we have an election coming up, the election will measure how the entire population is going to vote, but we very often anticipate what will happen in that election by collecting a sample, a smaller group of people, and learning some information about how they voted. So a sample is a smaller group that represents the whole larger data set, and so we study some trends in that sample, hoping that it is proportional to what's happening in the larger data set. Okay, so the first measure that we use here is called a standard deviation. It is represented with this symbol, which is a lowercase sigma. You've seen the uppercase sigma before. It looks like this. We'll use it again today. The uppercase sigma represents a sum, but the lowercase sigma represents what we call standard deviation. And standard deviation is a measure of how closely the values in a data set are grouped together. So we find the mean, which is kind of thought of as like the center of that data set, and we think, how far away from the center do all of the other data values spread out? So that is sigma. Today we're going to talk about how to calculate sigma, only because I want you to know that it's not magic. It comes from somewhere that we can actually calculate. We can calculate this using settings in a spreadsheet, like an Excel spreadsheet. We can calculate standard deviation using some tools in a scientific calculator, a graphing calculator, which most of us don't have, but you will if you take statistics as a class. You'll have a graphing calculator and you'll learn how to calculate this without having to do it by hand. The good news is for most of the work we do, we'll be given this value sigma, the standard deviation, and we won't have to calculate it ourselves like this. But let's go through this exercise one time so we see where these sigma values that they give us are actually coming from. So let's say, for example, we have this data set, 85, 88, 91, 96, and 100. They're 5 numbers. We don't know what they represent. Maybe it's the number of gumballs each person has, I was going to say, is holding in their pocket. Very large pockets, right? Okay, so first of all, we need to know the mean. Now, mean, median, and mode, those are measures of central tendencies that we've learned in other math classes. We know that to find the mean, now notice here, this is something you may not have seen before. In the statistics work that we do, we represent the mean with a symbol called mu. So expect to see mu as we move forward through our lessons. So we know from other math classes that to find a mean, which is otherwise known as an average sometimes, we literally add these together and then divide by the number of values in that set. So we have 1, 2, 3, 4, 5. So we'll sum these and then divide by 5. So 85 plus 88 plus 91 plus 96 plus 100, and then we divide that sum by the 5 values there. So if we sum across the top, that gives us 460 over 5. So 92 is the mean. So the idea of this sigma is that we want to get an idea of how far these other values are spread out from the mean, which is 92. Okay, so to find sigma, we take the square root of a fraction, where on the top, see that uppercase sigma? We remember from sequences and series, that means we're supposed to take a sum, right? So we're adding together So let's write some notes on here so we don't forget what's going on. That sigma means standard deviation. Zoom in here while we're writing. Okay, standard deviation. We know that this sigma means we're going to take the sum. This x sub I, so we're going to replace this I with 1, 2, 3, 4, all the way up through n, which means the last value in our set. So this x sub I represents a data value. So that x sub I for this particular problem will be 85, and then later it'll be 88, and then 91, and then 96, and then 100. So each one will take its turn standing in for x sub I. We know that this mu represents mean. We just talked about that, and we just found the mean for this particular problem. And that n on the bottom, just like when we're talking about sequences and series, it means the number of items in the data set here. Just like in sequences and series, n represented the number of terms in our series, right? Okay. So now let's return to our problem using this formula. So in the numerator, I'm going to take the sum of a data value minus the mean squared. And then plus, because we're taking a sum, another data value minus the mean squared, plus another data value minus the mean squared. Okay. So in my numerator, a data value, 85, minus the mean, mu, which we just found was 92, squared, plus, because I'm taking a sum. Now I do it with the next data value set, or the data value, pardon me, 88 minus the mean, 92, gets squared, plus the next data value, 91 minus the mean, 92, squared, plus the next data value, 96 minus the mean, 92, squared, plus the last data value, 100 minus the mean, 92, getting squared. So that sum is in my numerator. In the denominator, n represents the number of terms in our data set. That was just 5. So here I have the square root of 85 minus 92 is negative 7, gets squared, plus 88 minus 92 is negative 4 squared, 91 minus 92 is negative 1 squared, 96 minus 92 is 4 squared, and 100 minus 92 is 8 squared, divided by 2. This isn't hard stuff, right? It's kind of a pain in the neck, but it's not hard. Okay, so what we're taking is the sum, the square root of the sum. Negative 7 squared is 49, negative 4 squared is 16, plus negative 1 squared is 1, plus 4 squared is 16, plus 8 squared is 64, over, oops, I don't know why I put 2 there. That was supposed to be a 5, wasn't it? That looks better. Okay. So in my numerator, I grab my calculator and I add those together. I'll get 146 over 5. So let me see. If I grab my calculator and take 146 divided by 5, I get the square root of 29.2, and the square root of that is let's call it approximately 5.4. We'll see these standard deviations typically rounded to the nearest tenth. Rarely more precisely than that. Oh gosh, sorry guys, it was a little low. Okay. So that's a way to measure how far spread out these data values are from the mean, which acts like the center, 92. So what does that standard deviation actually tell us about the data set? Well, if this is how far it's spread apart, if that number gets bigger, it is more spread apart from the mean. If that number gets smaller, then it is less spread out from the mean. So a lower standard deviation means the data is grouped closer to the mean value. And if that standard deviation is higher, it means that our data is more spread out from the mean. Guys, I'm so popular. Let me turn my ringer off. Okay. Okay. So a data distribution is a way for us to visualize how that data is in comparison to one another. So what we'll do is group the data from a particular value to a particular value. We're building like a bar graph or a histogram here. Each of these is like a histogram, right? So it's a way for us to visualize how that data is grouped or clustered. So the data distribution is the way the data values are clustered. So looking at these histograms separately, can you see that if we group from some lower value all the way up to some higher value, and we show the number that fall into this group and the number that fall into this cluster and so on, can you see that the data in this particular distribution is lopsided, right? It falls very heavily to the left, and having it be lopsided is something that we called skewed. So we call this one positively skewed, where most of our data falls to the left of some center point. We call this one negatively skewed. But what we're going to see much more often in the work that we do is where we see a really nice symmetrical balance of data around some central value, which will be our mean. So this is what is called a normal distribution. Oops. And like I said, most of the work that we do will be involved with this normal distribution. So normal distribution is a symmetrical bell-shaped curve defined by the mean, which is mu, and the standard deviation, which is again sigma, of the data set. The area under the curve represents probability, where the total area is equal to 1. So we group probability and statistics together because they're very strongly related. And as we work over the next page with our with some problems involving this normal distribution, we'll see how it directly connects to probability. So because we know that the probability, the sum of all the probabilities of all the things that could happen has to equal 1, if I sum all of the areas of these bars, these separate regions of a normal distribution, what I find is that they total 1, because the probability that a value will have to fall somewhere under this curve is, well, it's guaranteed that it'll fall somewhere in that data set, so the probability is 1, because the total area is 1. All right, let's get into more specifics about this normal distribution. So the normal distribution, the way that data is distributed inside that normal curve, follows what we call the empirical rule. The empirical rule tells us in a normal distribution with a mean called mu and a standard deviation called sigma, approximately 68.2% of the data falls within 1 sigma of the mean. So here's the mean, which is in the center. If I fall within 1 sigma, that means I can go anywhere from going 1 sigma below the mean all the way up to 1 sigma above the mean. So when we say within 1 sigma, we mean anywhere from -1 to +1 sigma. So if 68.2% of the data in our data set, if it's a normally distributed data, 68.2% falls in that region. Well, you see how that's divided in half, with half of it above mu and half of it below mu, half of it above the mean, half of it below the mean. So if in total it's 68.2%, that means half of it, 34.1%, falls in this region, and the other half, 34.1, falls over here. So this is 34.1% of all of our data falls in this region, and 34.1% of all of our data falls in that region. Okay, next, approximately 95.4% of all the data falls within 2 standard deviations of the mean. So that means that going from 2 below the mean all the way up to 2 above the mean, that means in that region of our curve, 95.4% of the data will fall in that group. So if 95.4% of all the data falls in there, and I already know that 34.1% and 34.1% fall in here, well, let's grab our calculator and do some figuring here. Okay, so let me scoot this over so you can see it. All right, so 95.4% falls in this whole region, 95.4. And let me take out the 34.1% right here and the 34.1% right here. Remember, that was a total of 68.2%. No, I forgot to put some minus signs there. 95.4 minus 68.2, that leaves us with 27.2% to share between this region and this region. So if they're sharing it equally, because this is a symmetrical curve, then that means 13.6% of all of our data is in this region, and 13.6% of all of our data is in this region. So 13.6% here, 13.6% here. All right, and then approximately 99.8% of all the data falls within 3 standard deviations of the mean. So from mu down to -3 standard deviations, and then from mu up to +3 standard deviations. So 99.8% of all the data falls in there. So again, let's figure out exactly how much lies between -3 and -2 sigma, and how much lies between 2 standard deviations and 3 standard deviations. So this region in here that we already accounted for, remember that was 95.4%. So let's grab my calculator. So what I'm showing right here between my fingers falls within 3 standard deviations of the mean. That's 99.8. Now let me take out the part that we already knew, these 4 regions in the middle, which sum to 95.4. So I know that leaves 4.4% to be in these 2 spaces right here. So 4.4%, these 2 regions right here share it equally, so I divide that by 2. That means each one of these has 2.2% of the data. Okay, now, if that all represents 99.8% of all the data in our data set, and the whole data set is 100%, then what's left for these little regions out here? Well, the difference between 99.8 and 100%, there's only 2.2% left in there, right? So that 0.2% is shared equally by these very small regions on the end. So in this region down here, there's 0.1%, and this region over here, 0.1%. These percentages are going to be very important to us as we kind of use a normal curve to understand what percent of the data falls in a particular region on our curve. So let's see some examples here of how that works. So for each of these exercises, we're going to draw and label the normal distribution curve, then answer the following questions. So first, the weights of 50 football players are normally distributed with a mean of 178 pounds and a standard deviation of 8 pounds. So a mean of 178 and a standard deviation of 8. There are 50 players in total. So I'm not going to need that quite yet because right now I'm worried about the percentages. The percentages, again, follow this empirical rule. So let me start by filling in these regions. I know this one's going to be 34.1 and this one's 34.1%. These next guys are 13.6 and then 2.2 and out here 0.1 and out here 0.1. That's going to be the same for every normal curve we ever use. That empirical rule applies to all of them. Okay, but let's see what that means specifically for this particular problem. So mu is this value right in the very center of our normal curve. So mu, the mean, we have a mean of 178 pounds for a player. That's mu, the mean. So as we move out up 1 standard deviation, then up 2 standard deviations, then up 3 standard deviations, we're adding 8 more pounds, then 8 more pounds, then 8 more pounds. So I'll go 178 plus another 8 brings me to 186 pounds. That's plus 1 standard deviation. And then I'll add 4 more. So 194 pounds. That's plus 2 standard deviations. And then add another 8 pounds brings us to 202. That's plus 3 standard deviations. Now, if I go the other direction, I'm subtracting standard deviations from the mean, or subtracting 8 pounds from one region to the next. So 178 minus 8 pounds brings us to 170. That's minus 1 standard deviation. Then minus another 8 pounds brings us to 162. That's minus 2 standard deviations. And then minus another 8 brings us down to 154 pounds. That's negative 3 standard deviations. Okay, so now we're asked what percent of the players weigh between 178 right here and 194 right here. So from right here, 178 to right here, 194, well, I'm adding 34.1% plus 13.6%. So 34.1 plus 13.6 gives us 47.7% of our players fall, that was ugly. Okay, so 47.7% of our players fall in this weight region. Part B, what is the probability that a player weighs at most 170 pounds? Well, at most 170 pounds means it would be okay to weigh 170 or less to fit in this group. So here's 170 or less. So we're talking 13.6 plus 2.2 plus 0.1. 13.6 plus 2.2 plus 0.1. And if I sum those, I get 15.9% of our players fall in that weight region. Part C, what's the probability? Oh, so here I should have mentioned before. So when we say the percent of the data that falls in a particular group, it correlates to the probability that a player falls in that group. So for example, if I were to pick one player at random out of all 50 football players, the probability that that player that I pick would be at most 170 is 15.9%. That's the probability that the player falls into that group because that's the percentage of the players that fall into that group. So they have a really direct correlation that's easy to follow there. Okay, so what's the probability that a player weighs less than 162 or greater than 194? So less than 162, so that means down here. So 2.2% and 0.1%. 0.1 and 2.2. Or, so we're going to add that to what's happening above 194, greater than 194. So above 194, that's 2.2 plus 0.1. Okay, so if I add those all together, what I'll get is 4.6%. Now, that's a pretty low probability, right? Remember that probability ranges from 0 to 1 or from 0% to 100%. So 4.6% is a pretty low probability because we're talking about the outliers here that are in this very narrow part of the curve, very far away from the mean. It is much less likely that something lands in this part of the curve than closer to the mean in those bigger groups. Now, we've been talking about percentages, but now we want to know how many players weigh between 170 and 186. Okay, so 170 to 186, we're talking within 1 standard deviation there, right? So 34.1 plus 34.1. So that gives us 68.2%. But they didn't want to know what percent here. They didn't want to know what probability. They wanted to know actually how many players that was. So 68.2% of the 50 players. So 68.2%, I'm going to remember in its decimal form, that's 0.682. I just moved that decimal point 2 places to the left. 68.2% of 50 So I grab my calculator, 68.2 times, nope, 0.682 in its decimal form, right? Times 50 gives me 34.1, or about 34 players. We'll round down here because we can't actually have 0.1 football players. Okay, so now let's do some more on a different problem. Mrs. Fuller recently tested her 120 keyboarding students, so that's the total number of students in our data set, to see how many words per minute they can type. The results were normally distributed with a mean of 45 and a standard deviation of 6. Mean of 45 and a standard deviation of 6. Why don't you take a moment, like a whiteboard problem, to pause the video and label this curve the same way that we have for the previous problem. So tell me what percent falls in each of these groups. That's going to be the same as the empirical rule told us for every problem. And then set up the mean in the middle, and then show what 1 standard deviation and 2 standard deviations and 3 standard deviations out from the mean would be. So pause here, do it, and come back. All right, does your normal curve look like mine? Check your percentages in each group. Check and make sure you put 45 for mu in the center, and then up 1 standard deviation is 51, then 2 is 57, then 3 is 63. Or from the mean going down 1 standard deviation is 39, down 2 would be 33, down 3 would be 27. Okay, so now let's answer some questions about that. We want to know about how many students can type at least 39 words per minute. So that means 39 words or more, right? Let's find 39 right here. So we want 39 or more, so everything above that. So 34.1% plus another 34.1% plus 13.6% plus 2.2% plus 0.1. So if I sum that, I'm going to find 84.1%. But notice they didn't want to know what percent, and they didn't want to know what probability. They wanted to know actually how many students that means. So 84.1% of the students in Mrs. Fuller's classes, and there were 120 of them. So 84.1% in its decimal form, 0.481, times the total number of students, 120. So I'll grab my calculator, 0.841 times 120 gives me 100.92. Again, we're going to round that down to the nearest whole keyboarding student. Nobody wants 92.92 of a keyboarder, right? We want whole students here. So about 100 students. Good. Okay. Now, about how many students can type within 1 standard deviation of the mean. So here's the mean. Remember that within 1 standard deviation means I can go down 1 standard deviation from the mean, or from the mean go up 1 standard deviation. So we're talking about that region in there. Now we know within 1 standard deviation, that means 68.2%, right? 34.1 plus 34.1. The empirical rule at the top of the page told us that would be 68.2%. But we don't want to know what percentage of the students. We don't want to know what's the probability that if I picked 1 student, they would fall in this region. We want to know how many students can type within 1 standard deviation of the mean. Remember, that means in particular for this problem that we're typing between 39 and 51 words per minute. So what is 68.2% of Mrs. Fuller's students? So if I grab my calculator, 0.682 times 120 gives me 81.84, or about with a U, 81 students. Now, finally, students need to be in the top 2% in order to be eligible for the national typing competition. If Carla can type 56 words per minute, is she eligible? Okay, so look at our words per minute here across the bottom of our curve. Carla can type 56 words per minute, which means she's kind of right here, right? Does that fall within the top 2%? Well, look at where she is. What's above her? Above her, we have 2.2 plus 1 appears 2.3% of people are above her. If 2.3% of the people are above her, is she in that top 2%? Nope, she falls just below the top 2.3%. So we'll say, no, Carla's not in the top 2%. Feeling pretty good? Okay, so your homework is to do a lot of practice, not a lot of practice, but to do practice on this normal distribution using our empirical rule, much like the problems we have here. See you later.